Hi and welcome to John's Maths book. In this video, we're going to be looking at finding the area of a segment of a circle using double integration. If you like the video, then please hit the like button and I'd be delighted and honoured if you'd subscribe to the channel. Without further ado, let's go over to the whiteboard. In this exercise, we have a circle cut by a line. The segment cut from the circle is shown in blue. We are tasked with finding the area of the region marked in blue using double integrals and polar coordinates. The equations of the circle and the line that cuts it are shown. The circle has a radius of 1, cuts the x-axis at x equals 2, and is symmetrical about the x-axis. The line cuts the x and y-axis at 1 and has a gradient of -1. Let's begin by converting the equations into polar coordinates. To do this, we'll substitute r cos theta for x and r sin theta for y. To understand why we do this, take a look at one of my earlier videos which goes into detail. I'll post a link to it in the description. Starting with the circle, replacing x with r cos theta and y with r sin theta, we get r squared cos squared theta plus r squared sin squared theta is equal to 4. Now if we remove the factor of r squared, we're left with r squared into the bracket of cos squared theta plus sin squared theta equals 4. Using the trig identity, cos squared theta plus sin squared theta is equal to 1, we're left with r squared is equal to 4. And taking the positive square root of both sides of the equation, we're left with r is equal to 2. And now if we look at the line x plus y is equal to 1 and substitute r cos theta for x and r sin theta for y, we have r cos theta plus r sin theta is equal to 1. If we take r out as a common factor, we have r into the bracket of cos theta plus sin theta equals 1. And dividing both sides of the equation by cos theta plus sin theta leaves r is equal to 1 divided by cos theta plus sin theta. Now let's take a look in more detail at what happens when we sum infinitesimally small sectors of area in the r direction, which will represent our inner integral. This diagram represents a sector of the region capital R. The angle it makes is infinitesimally small and is denoted by d theta. Within the sector, we have infinitesimally small pieces of area denoted by dA. The size of each piece of area is the height multiplied by the width. So in this case, dr is the height and r d theta is the width. So dA equals r dr d theta. To find the total area of the sector, we integrate or sum in the r direction. For this exercise, when we sum or integrate in the r direction, we begin at the point where the line cuts the circle. So where r equals 1 divided by cos theta plus sin theta. And we end at the point where r reaches the circle. So that's at r equals 2. We can now define our inner integral. We're integrating r dr and our lower limit is r equals 1 divided by cos theta plus sin theta. So that's the line that cuts the circle. And our upper limit is r equals 2, so where it meets the circle. Now let's find the limits of the outer integral. So that's when r rotates about the angles of theta. To do this, let's first visualize what happens as r rotates about theta across the region capital R. As r rotates through theta, it begins at a negative angle and advances to a positive angle of theta. Each sector represents an angle of d theta. By summing each of the infinitesimally small sectors, we get our total area. We do this by integrating from the negative angles of theta to the positive angles of theta. The angles represent the upper and lower limits of the outer integral. To find the angles, we need to solve our two equations for theta, as this will represent where the line cuts the circle. So our two equations are r equals 2 and r equals 1 divided by cos theta plus sin theta. Now if we substitute r equals 2 into equation 2, we have 2 equals 1 divided by cos theta plus sin theta. Rearranging this gives cos theta plus sin theta is equal to 1/2. If we now multiply both sides of the equation by the square root of 2 divided by 2, we have the square root of 2 divided by 2 times cos theta plus the square root of 2 divided by 2 times sine theta is equal to the square root of 2 divided by 4. Now the square root of 2 divided by 2 is the sine of pi by 4 and the cos of pi by 4. So substituting these values into our equation, we have the sine of pi by 4 times cos theta plus cos pi by 4 times sine theta is equal to the square root of 2 divided by 4. We can now use the trig identity sine A times cos B plus cos A times sine B is equal to sine of A plus B. If we apply this to our equation here, we get the sine of pi by 4 plus theta is equal to the square root of 2 divided by 4. And therefore theta is equal to arc sine of the square root of 2 divided by 4 minus pi by 4. Now if we remember that there are two angles in the range 0 to pi where the sine of the angle is the square root of 2 divided by 4, the other angle in this case is pi minus arc sine of the square root of 2 divided by 4. So our other value of theta is pi minus arc sine the square root of 2 divided by 4 minus pi divided by 4. So we now have our double integral. The outer integral starts at theta equals arc sine of the square root of 2 over 4 minus pi by 4 to theta equals 3/4 pi minus arc sine of the square root of 2 divided by 4. And then the second integral starts at r equals 1 divided by cos theta plus sine theta and goes to r equals 2, and we're integrating r dr d theta. Now let's evaluate our integrals. So let's begin with the inner integral. So we're integrating r dr from r equals 1 divided by cos theta plus sine theta to r equals 2. So the antiderivative is r squared divided by 2, evaluated from 1 divided by cos theta plus sine theta to 2. So if we plug in our upper limit of 2, we get a value of 2, and then we subtract the lower limit, and when we plug this into our antiderivative, we get 1 divided by cos theta plus sine theta squared multiplied by 2. Now let's simplify the expression cos theta plus sine theta squared. So if we expand it out, we get cos squared theta plus sine squared theta plus 2 cos theta sine theta. Now we know that cos squared theta plus sine squared theta equals 1. And we can break 2 cos theta times sine theta up into cos theta times sine theta plus cos theta times sine theta. Now if we use the trig identity, sine A times cos B plus cos A times sine B is equal to sine of A plus B, we're left with 1 plus sine 2 theta. Our inner integral therefore evaluates to 2 minus 1 divided by 1 plus sine 2 theta multiplied by 2. Now moving on to our outer integral, we can split this into two separate integrals. So the first is 2 d theta from theta is arc sine the square root of 2 divided by 4 minus pi by 4 to 3 pi by 4 minus arc sine of the square root of 2 divided by 4, and that's minus the integral of 1 divided by 1 plus sine 2 theta times 2 d theta between the same limits. The antiderivative of the first integral is 2 theta, and without going through the various steps, the antiderivative of the second integral is minus 1 divided by tan theta plus 1 times 2. This equates to 2 theta plus 1 divided by tan theta plus 1 times 2, and we need to evaluate it between arc sine of the square root of 2 divided by 4 minus pi by 4 to 3 pi by 4 minus arc sine of the square root of 2 divided by 4. If we now plug our upper and lower limits of theta into 2 theta, we get 2 pi minus 4 times arc sine of the root of 2 over 4. And if we do the same for 1 divided by tan theta plus 1 times 2, we get a value of minus 1.322. And this gives us our final result.